So just as a little flashback, so you might want to skip ahead to calculations because I'm about to start drawing, but to remind you of what you know about titrations from grade 11, okay? This thing is your burette, and again, some of this will help with question interpretation, okay? So again, if you've had this lesson already in class, you could skip ahead for sure to the calculations, okay, if you want to see more sample problem. Your titrant, is in your burette, and typically, but not always, you're going to have your base in the burette, but again, not always, okay? And then what you are titrating is, again, in an Erlenmeyer flask, typically the acid, but not always, okay? So you'd have a sample of an acid in this Erlenmeyer flask. You would titrate it with base, and in terms of terminology, there's something called the equivalence point, okay, where your acid, and there's other types of titrations as well, but our focus is on acid-base titrations. At the equivalence point, your acid and base are in what we call stoichiometric amounts. If it's a 1-to-1, what that means is moles of acid are equal to moles of base, and they perfectly consume each other, okay? But it depends on the ratio, but basically, again, they perfectly consume each other or use each other up at the equivalence point, so you have no acid or base left in that system from what you initially had in your Erlenmeyer flask or in your burette, okay? There's also something called the endpoint. These terms are different but similar to one another. The endpoint, really, we're talking about the indicator itself, okay? In order to see the reaction happening, basically you're going from clear and colorless up here to clear and colorless down here. In order to see when you've hit that equivalence point, you need an indicator that has an endpoint that is close to the equivalence point, okay? In order for that indicator to show what you wanted to show, which is when you are actually at that equivalence point, okay? The indicator that we used last year was phenolphthalein, okay? That would be a good indicator to use when you have a strong acid and a strong base, because when you have a strong acid like hydrochloric acid and a strong base like sodium hydroxide, you end up with water and NaCl, okay, some sort of salt, and the pH is neutral, and phenolphthalein has an endpoint that is close to the equivalence point of this system, a neutral pH, so it would change color about 8.2-ish, okay? So again, that's why last year we wanted you to hit the point where you just started to see that pink color, and that would be closer to a pH of 7, okay? The situation is when you have a weak acid or a weak base involved in a titration, you have to worry about the equilibrium system, so that's where we're heading. Okay, so I think the best way to do this is just with a sample problem. So I'm going to do a weak acid and strong base titration to start. Okay, for no particular reason, but this one maybe is a little bit of an easier one. Okay, so I'm going to take a second and put a question up here. Okay, so here's the question. I kind of took this from the sample problem on page 600, but I changed one of the concentration values, but you can always kind of follow along and just realize I've changed the concentration value from the textbook, this one right here, for no particular reason other than it, like, I don't want to kind of mislead you to make certain assumptions that if they were the same value, then you might be tempted to make, okay? And this is just any old monoprotic acid. We're not doing polyprotic titrations. This, though, is weak. In your textbook, they have acetic acid, so you can pretend that this is acetic acid because we are going to need the K value for this at some point in the next 10 seconds or so. So you want to know the pH of each solution before you even start titrating. So for your sodium hydroxide, this becomes really easy as long as you realize that this is a strong base. This is not an equilibrium question at all. So what is the pH of 0.25 moles per liter sodium hydroxide? Well, I can get the pOH no problem by just taking the negative log of your 0.25 and kick that over to a pH. So I'm doing it right now. Negative log of 0.25 is 0.60. Subtract that from 14. I get a pH value of 13. I'm looking at sig digs here. 40, two numbers after the decimal place, corresponding to 2 sig digs in your concentration information. This would be a multiple choice question, not the titration one, but this part would be a multiple choice question on your test, right? For your weak acid, because it is weak, you need to consider the equilibrium system when you're thinking about pH. So you have 0.30, so I'm setting up an ice table really. 0 because we're ignoring autoionization of water, and 0. Okay, at equilibrium, 0.30 minus x, and x. You're going to set this up to the Ka of, and again, we're pretending that this acid is acetic acid. Okay, acetic acid, 1.8 times 10 to the power of -5 is your Ka value. You're going to have x squared over 0.3, technically minus x, but if you divide 0.3 by that Ka value, you can see that you can disregard it with the 100th rule. So I'm going to kick that over to a pH. So you are solving for x, which is the proton concentration. So 1.8 times 10 to the power -5 times 0.3, don't you love how I'm doing this out loud? Take the square root of that, answer the negative log of that answer. I get a pH value of 2.63 for your sig digs. These numbers make sense. Your base is basic, your acid is acidic, okay? That's before you even do anything, all right? Now, I want part B. I want what is pH. Let's again follow that, maybe the textbook as an exemplar. 10 mils of your base added. So what is the pH after the addition of 10 mils of sodium hydroxide? I'm going to quickly go back and check the concentration of sodium hydroxide because I forget already. Okay, your sodium hydroxide concentration we said was 0.25 moles per liter. This is just a reminder, okay, from the preceding information. And your acid, so you have 20 mils of your acid, and your acid concentration, we went with the textbook one, is 0.30. This is just for my information, so I don't have to keep flipping back and forth if I forget these values, okay? So when you're thinking about solving a titration that is in the process, okay, so remember part A was before anything happened, consider it being two parts. Part 1, you're dealing with the stoich, okay? Part 2, you're dealing with the equilibrium. The reality is the stoich and the equilibrium are happening simultaneously, but mentally and mathematically, it's much easier to think about them as happening kind of one after the other. So there's going to be a stoichiometric reaction first, and then whatever is the result of that stoich is hopping into an equilibrium system. Think about it that way only, okay? Otherwise it's going to get too crazy. So you have an acid in your Erlenmeyer flask. You're mixing base, you're adding base a little bit at a time to that acid. So this is not an equilibrium system. This is your stoich part, right? This is your acid-base reaction. Think about what's happening when you're dumping that base in. You're adding a bunch of hydroxide, okay? So I'm up over here now. You're adding a bunch of hydroxide to that system. That hydroxide, and don't forget as well, you do have a weak acid equilibrium system when you have the weak acid, but there's still protons, right? So even if there's a low percent reaction, this hydroxide that you're adding from the base is going to react with these protons and continuously shift this equilibrium system to the right, okay? So it doesn't matter that this is a weak acid, it's still going to quantitatively react with that base in an acid-base reaction, okay? Just like last year, but instead of HCl, it's H some other anion, okay? In this case, it's acetic acid, so it's acetate, okay? So you can get water, okay? You're going to get sodium acetate, or whatever the anion is of that weak acid, okay? Again, in this sample problem, it's acetate, okay? So this is not a nice table. This is my stoic. I have a concentration of 0.25 moles per liter of my sodium hydroxide. I have a concentration of 0.30 moles per liter of my weak acid. I have a volume of 20 mils, or this many liters. I have a volume of 10 mils, or this many liters, okay? You're not at the equivalence point, and the reason that you know this is because it's a one-to-one reaction. You've added fewer mils at a lower concentration of base than what you have of acid. So this is the excess reactant. This is the limiting reactant, okay? So your limiting reactant is fully consumed. And if you don't see that, let's calculate the moles of each, okay, so that we can really see it. The moles is going to be your concentration times your volume, which I believe is 6 times 10 to the power of negative 3. This will be 2.5. Did I do that right? Times 10 to the negative 3. So in this one-to-one ratio, 2.5 times 10 to the power negative 3 would use 2.5 times 10 to the power negative 3 of this acid, okay? So that, again, further proves that that's the limiting reaction if you didn't see that right away, okay? So I'm going to calculate the number of moles of my acid that are left over just by subtracting this 6 times 10 to the power negative 3 by this 2.5 times 10 to the power negative 3. So correct me if I'm wrong, but I believe you get 3.5 times 10 to the power negative 3 moles of this left over, okay? So this is reminding me of the strong acid, strong base reaction questions that we did towards the beginning of this acid-base chapter. You're going to have, or you expect to have, an acidic solution because you have moles of acid left over, but there's a little bit more to it than that because you have, and again, these moles, what we're about to do is kick it over to a concentration. So let's do that first. Let's get the concentration of the acid that is remaining, okay? I'm going to take that molar value, 3.5 times 10 to the power of negative 3. I'm going to divide by, so this is moles, total volume. So common mistake, whoops, there we go. Don't forget, you're adding these two things together, so my total volume is 0.030 liters. So my concentration of my acid that is remaining is 3.5 times 10 to the negative 3 divided by, yes, I'm plugging this in, 0.117, let's say. 0.117 is probably good enough moles per liter, okay? I'm going to put a circle around this so I don't lose it. This is hopping now into an equilibrium. So remember, we're doing stoic first, okay? Then we're plugging our stoic calculated concentrations back into an equilibrium system. So this is my weak acid that is remaining, and because it's weak, it's going to hop into an equilibrium system. Okay? Now, I'm going to clear a spot. So I tried to clear a little spot at the top here. I'm going to, because I want to keep all of this on the same page so that we can see everything at once. But here's our equilibrium system, okay, for my weak acid. Again, I want to know the pH at this point, so I want to solve for proton concentration, okay. My initial concentration of weak acid is 0.117. This is what remains after the stoichiometric reaction, okay? My protons are 0 because I'm disregarding autoionization of water, and What I'm interested in though is this, okay? So put a star here and say a lot of people forget this. What I'm talking about is the acetate that you produced through the stoic. This is sodium acetate, okay? As is solution, so separate ions. So this acetate will have an impact on the equilibrium, okay, because it's in here, right? This is not a zero, okay? It's part of this equilibrium system, and you produce some in your stoic, okay? So the concentration of acetate that you produce is the moles that you produce divided by that total volume, okay? The moles that you produced are based on the limiting reactant, which was your sodium hydroxide, okay? So this 2.5 times 10 to the power negative 3 value is your molar amount of acetate that you have produced from your stoic. Again, it's a 1-to-1 ratio, so 2.5 times 10 to the negative 3 moles of sodium hydroxide will produce 2.5 times 10 to the power negative 3 moles of acetate. Total volume still your 30 mils, okay? So the concentration of your acetate is 2.5 times 10 to the power negative 3 divided by 0.03, 0.083. That's a molar concentration, so moles per liter. I'm going to plug it in up here. Okay, so what did I say it was? 0.083. Okay, now I'm running out of space, so I am going to go to the next page. So again, keep an eye on what you want. You want the pH at this point. It's going to shift to the right because again, we're disregarding the auto-ionization of water. It's too small. So this, I want X, okay? That's an X right there, okay? Now, just like before, I can disregard this X. What I really should do though first is look up the Ka value of acetic acid, because that is what this weak acid is. The Ka of acetic acid is 1.8 times 10 to the power negative 5. Okay, that is small enough. Again, you can check 0.083 would be your worst case scenario of what concentration would be most affected by that X. 0.083 divided by that Ka is definitely going to be bigger than 100. So this expression becomes 0.083 X divided by 0.117. Your X is your proton concentration. Kick that over to a pH value, and then you are done. So 1.8 times 10 to the power negative 5 times 0.117 divided by 0.083. Proton concentration is 2.54 times 10 to the power negative 5. I still have the number on my calculator though, so I'm going to take the negative log of that number. I get a pH value of 4.60, okay, to 2 decimal places, which makes sense because if you look back at the initial pH value of that acid, now you're a little bit higher, I hope, okay? I forget what the actual number was, but you're a little bit higher because you added base, okay? Next part. Okay, part C, again, using the textbook as kind of a template, even though I've changed that one concentration. The numbers aren't going to match up. The process will. I want to know the pH at the equivalence point, not the equilibrium point, okay? This means equivalence point. We defined that earlier. So, again, we're looking at this as being two components. We're going to look at the stoic first. Then whatever happens after the stoic, we're going to plug into an equilibrium system. That's appropriate, okay? Up here, this is the data, okay? So again, you have your sodium hydroxide in the burette. You have your acid in the Erlenmeyer flask. You have 20 mils of a 0.3 mole per liter acid, and you're titrating that with 0.25 moles per liter base. So you need to interpret what this means at the equivalence point. What does that mean? So you have your stoichiometric reaction, your acid-base reaction, okay? And here's what's happening, okay? The definition of equivalence point is these are in stoichiometric amounts, okay? And because this is a 1-to-1 ratio, stoichiometric amounts would be exactly equal molar amounts. I already calculated the moles of the weak acid that I have, which is just based on the concentration and the volume. So my concentration is 0.3, my volume is 0.02 liters, okay? So my molar amount of my acid is my 6 times 10 to the power negative 3 moles. We've seen that number before, okay? So the equivalence point means I have added exactly the same number of, again, it's because it's 1-to-1, it's exactly the same number of moles of base. Okay, I know the concentration of the base. What I'm going to calculate is the volume of base that would take me to that equivalence point. Okay, so C equals N over V, V equals N over C, right? So I'm going to take that molar amount, okay, and divide it by your concentration, okay, and then see if that makes sense. I get a volume of 0.024 liters, okay, and it does make sense because I have a slightly greater concentration of acid, 20 mils, okay, slightly lower concentration of base, 24 mils would take me to that same molar amount, so that seems like a reasonable value, okay. Now again, make sure you understand what the equivalence point means, okay? The equivalence point means that's gone, okay? Now before, when we had strong acid, strong base, titrations, the equivalence point was at pH 7, right, where you just had water and something like NaCl, okay, if it was sodium hydroxide and hydrochloric acid. The problem here is you're making something that's going to have an effect on the pH, okay? So even though you're consuming both of your reactants, you need to think about what you're making. Again, you're making, whoa, that's blobbier than I hoped for. You're making acetate, okay? So I want to know what concentration of acetate I'm making. Now, as a side, if I was making NaCl, we've already talked about salts, right, and their effect on pH. It depends on what they're made of. In this NaCl, chloride's not going to affect the pH, sodium's not going to affect the pH, so that's why NaOH plus HCl at the equivalence point would be a neutral solution, right? But here, my acetate is going to affect the pH. So I make 6 times 10 to the power negative 3 moles of my acetate based on that 1-to-1 ratio, okay? Divide by the total volume. That's the only reason that I solve for that volume. My total volume is, what, 0.044, yeah, 44 mils, okay? So I'm going to calculate my concentration of my acetate. This is going to hop into your equilibrium, 0.136 moles per liter, okay? So we've dealt with the stoic part. I'm going to put this in an equilibrium system. Okay, so on the preceding slide, remember, we made some acetate in our stoics. So at the equivalence point, even though both of my reactants were totally consumed, I made some acetate. This acetate is the conjugate base of the weak acid, acetic acid, so it's going to act as a base in solution. It's going to take a proton from the water and release hydroxide. So I expect that my pH at the equivalence point should be a basic pH, should be greater than 7. So I'm disregarding water in my ice table because it's a liquid, okay? I'm pretty happy putting 0 in here. Don't be tempted to put anything to do with your original weak acid solution in here because you use it all up, right? That's the definition of equivalence point. We're disregarding autoionization of water. You're at equilibrium, so you're going to be minus X. You're going to be X and X, okay? I want the pH, so I want that hydroxide ion concentration. This time, though, I have a Kb situation, right? And you recognize that because you see hydroxide on the right-hand side. So I need the Kb for your acetate, which I can get from the Ka of acetic acid, okay? The Ka of acetic acid is, what do we say it was? 1.8 times 10 to the power of -5. Kick it over through a KW, so KB is going to be KW over that KA value. So my KB, I believe, will be 5.56? I better check it to make sure. 1 times 10 to the power -14 divided by, yeah, 5.56 times 10 to the power -10 is going to be equal to x squared over 0.136. I can safely, check it, but 0.136 divided by something times 10 to the power -10 is going to be significantly greater than 0, so I can disregard this, okay? Solve. Recognize, though, that you are solving for hydroxide. Common mistake is to get confused and kick this over and call it a pH, okay? But let's do it. 5.56, 10 to the -10 times your 0.136, square root of that. I get a hydroxide concentration of 8.69 times 10 to the -6. Negative log of that, I get a pOH of 5.06. Subtract that from 14. Don't forget that part. I have it because you're looking for a basic solution, right? So that's not the pH. The pH is 14 minus 5.06, or 8.94. It makes sense. It's basic, okay? So you're at the equivalence point, but you have a basic solution, not a neutral solution, because you create something in your stoich that hops into an equilibrium and releases hydroxide from water, because what you create is a weak base of acetate. The last part of the textbook question asks you really to over-titrate, and it asks you for a pH beyond the equivalence point. So it says something like it doesn't even give you any values. So just realize that if I over-titrate, so if I add, I don't know, tons of sodium hydroxide, that's going to use up all of the, so again, just qualitatively, okay? So if your sodium hydroxide is in excess, all of this will be gone. Sure, you're going to produce some acetate through your stoich, which is going to hop into the equilibrium, but the equilibrium system is really not going to be that important for pH, because this kind of trumps it. This massive amount of hydroxide is what you're going to use to calculate the pH, okay? So really it's not an equilibrium situation anymore. Theoretically, technically, this equilibrium system is happening, but its contribution to the hydroxide ion concentration, because it would still act as a weak base, would be insignificant compared to the amount of excess hydroxide you have physically added to that solution. Okay, so that's more of a theoretical question. Okay, last titration question, so just a different spin on it. You got a weak base and a strong acid. I'm not going to bother with the pH before you start. The acid's pH is just going to be the negative log of 0.1 because it's strong. The base's pH, you got to plug in that 0.15 ammonia into an equilibrium, set it up equal to a KB. Okay, that's not the tricky part. So let's do a part A. You know what? I'm not going to do before the equivalence point either. I'm just going to do the equivalence point. Okay. So let's do and it's not a stretch for you guys to take this to before the equivalence point. Just use this. What I'm about to do is a template plus the preceding stuff. So what is the pH at the, that's an at sign, equivalence point? So again, you're thinking stoich first, then popping stuff into an equilibrium second. So the stoich is this. You've got your base, you've got your strong acid. It's a quantitative process, so this is not the equilibrium system you're looking for. The base will take a proton from the acid, leaving it just chloride ions, okay? And at the equivalence point, none and none, okay? But you have made something that is going to have an impact on that pH. Not this. This guy's, my chloride, is going to have no impact on the pH, okay? So I'm going to use my concentration and volume of my ammonia to get moles of ammonia. Your moles of ammonia will be, what, 0.02 times 0.15, which is going to be 3 times 10 to the power negative 3. Again, tell me if I'm wrong and I won't be able to hear you, okay? At the equivalence point, same molar amount of HCl. That's the definition of equivalence point. So I'm going to solve for the volume of HCl that is required, okay? So I'm going to take that 3 times 10 to the negative 3, divide by your concentration. Yes, I just plugged that into my calculator. The volume is 30 mils, or 0.030 liters. Okay, again, that makes sense. The HCl has a lower concentration, so you'd expect a greater volume of it to be needed to contain the same molar amount. Okay, now what I'm more interested in is what the concentration of ammonium is that I have produced. Okay, I am going to have 3 times 10 to the power negative 3 moles of ammonium from my 1-to-1 ratios. Okay, divide by the total volume. Again, that's the only reason why I calculated this volume in the first place. The total volume is now 50 mils. Okay, so the concentration of ammonium is 3 times 10 to the negative 3 divided by 0.05, 0.06. Again, I plugged that into my calculator. I'm not ashamed. Moles per liter. This is what's hopping into an equilibrium system. Okay, so here's my equilibrium system. I have produced some ammonium, which is the conjugate acid of the weak base ammonia. It's going to act as an acid, dump off a proton to form its conjugate base. Okay, so in your ICE table, you're going to have 0.06. You're going to have 0 because you've used up all of this acid, right? Because you're at the equivalence point. You're going to have 0 because you've used up all of this base because you're at the equivalence point, right? So at equilibrium, I've got this, that, and that. I need to set this up to the Ka of ammonium, okay, which you get from the Kb of ammonia. Okay, so I'm not going to get the whole thing here, but you're taking the Ka of your NH4 plus. You're going to set that up equal to x squared over your 0.06. Even though 0.06 is pretty small, if you compare that to your calculated Ka value, once you look up that Kb of ammonia, you can disregard this x. Be prepared to explain that on a test, but we've used the 100th rule a million times before. So rearrange, solve for x. Recognize that x will be your proton concentration. Kick that over to a pH. And I would expect to have an acidic pH in this situation at the equivalence point. So weak base, strong acid, acidic pH at the equivalence point. The reverse of that, if I had a strong base, weak acid, I had a basic pH at the equivalence point. Okay, so calculating pH at the equivalence point is actually a little bit easier than calculating it before the equivalence point. But I'm not going to do that for this example. You have an example already with the weak acid situation. I'm never going to ask you for weak base and weak acid titration. You could do it. You have the skills, but we're not going to go there. That's for next year for you guys. Okay?